Welcome to EPG Pathshala. In this session, we will be discussing about special triggering devices. Special triggering devices are used for thyristor triggering. There are various types of triggering devices which are available in the market. Previously, we have already studied special triggering circuits using bipolar junction transistors and FETs. But the main disadvantage of this circuit is that component count. Component count of this circuit is very high. You require so many components along with your transistors. So therefore, special triggering devices are generally preferred. These devices possesses the negative resistance region. Negative resistor region plays important role for reducing the count of the component. There are various types of triggering circuits which are used for thyristor triggering, mainly monostable multivibrator, pulse generator and relaxation oscillators. Relaxation oscillators is widely used circuit for the triggering of the thyristors because it has very low component count. Some of the thyristor triggering devices we will be studying in this session. There are many devices, but for the time limit we are discussing 8 to 9 types of special triggering devices. One can classify thyristor triggering devices by many ways. We will classify the thyristor triggering devices as two-terminal devices, unijunction transistors and multi-layer control devices. Let us see the list of these devices. Two-terminal devices which are widely used are Shockley diode, DIAC, that is diode for alternating current, and asymmetric AC trigger switch, which is denoted by ST4. It is also one type of DIAC. There are two types of unijunction transistors which are widely used. Those are unijunction transistor, which is denoted as UJT. Second is programmable unijunction transistor, it is PUT. There are multi-layer devices which are also widely used. Those are silicon unilateral switch, silicon control switch and silicon bilateral switch. Along with this, so many thyristor triggering devices are generally used. First we will see the Shockley diode. It is the most simplest type of diode. It is two-terminal semiconductor devices. It has low current and low voltage. Its switching voltage is low. It is unilateral, hence used for half wave operation. It is also used for SCR triggering. Figure shows the symbol of the Shockley diode, structure of the Shockley diode. It has 4 layers PN. It has anode and cathode. There are 3 junctions J1, J2 and J3. There is no control terminal, so one can say this is uncontrolled device. It switches at a particular voltage. If we see the equivalent circuit of this, it is similar to SCR but without gate. One can consider it is a combination of two transistors, one is PNP and second is NPN. This is the characteristics of Shockley diode. One can see it looks like SCR IV characteristics, but it has difference. There is no gate triggering here because it does not have gate terminal. There are various parameters we can observe on the IV characteristics, that is IF is the rated forward current, IH is the minimum holding current, VR is the reverse breakdown voltage and VBO is the breakover voltage in forward bias condition. When it reaches to VBO, it automatically turns on. Till that voltage, it is turned off. So this is the simple characteristics of Shockley diode. Hence, one can see that there is negative resistance region similar to SCR. So, main application of Shockley diode is relaxation oscillator. One can see the simplest diagram of Shockley diode relaxation oscillator. There is source, one resistor, one capacitor and Shockley diode. It means you require only two external components. If you see the operation, initially when power is on, capacitor will get charged till the breakover voltage VBO. When it reaches to breakover voltage, it will discharge through Shockley diode because it will turn on. The waveforms of relaxation oscillator are shown in the figure. You can see it will give sawtooth type of waveform showing capacitor charging and discharging. Nowadays, people don't much prefer Shockley diode. Its use is reduced. Diode, it is a diode for alternating current. This name is given because it is a bidirectional device. It is also referred as bilateral trigger diode. It has two terminals, anode 1 and anode 2. Since it is symmetric, the names are given like this. It is a low current, low voltage switching device. It is a bilateral, hence it is used for half wave control, full wave control of SCR and triode. It has three layer structure, either NPN or PNP. There is no control terminal. It has two junctions J1 and J2. It is simple structure with two junctions J1 J2. If you see the diode characteristics, it is shown as IV characteristics of diode. There are various parameters one can see in the characteristics, that is rated forward current, reverse current, reverse breakdown voltage, forward breakover voltage. VBO and VR is generally same. So, it is symmetrical type of device. From the diagram, it is clearly seen. So, this is a very low power device because it is only used for the triggering of the circuit. It cannot handle very high power. Typically, this voltage VR and VBO is typically 20 to 40 volt. In the market, generally 20 to 30 volt diode is widely used. Diode can be used in various types of circuits. Mainly, it is widely used in light dimmer circuit or fan regulator. One can see the circuit diagram of light dimmer circuit in which triac is used, in which there is phase shifting network of RC is shown in the figure, and the capacitor voltage is not directly given to the gate of the triac but through diac as shown in the figure. One can see the timing waveforms of this circuits. So, input is sinusoidal. If you turn on the supply, then capacitor will charge through R and load. When it reaches to approximately diac voltage, then diac will turn on as seen in the characteristics of diac. When it turns on, it will trigger the triac. When it triggers triac will be turned on and you will get the voltage to the load. The load voltage is also shown in the timing waveforms. Since triac is also bidirectional device, you will get the bidirectional voltage which will vary according to the value of R, because R is varying. If you set value of R, you can set the delay angle or phase angle. This is called as phase angle control. Now next, to two terminal devices is asymmetric AC trigger switch. It is called as ATS. Sometimes it is also called as ST4. It is similar to DIAC but slightly different. DIAC is symmetric device. This is asymmetric device. If you see the equivalent circuit, it is nothing but SBS, silicon bilateral switch. We will be studying it afterwards in series with Zener. So Zener makes this asymmetric. If we see the ST4 characteristics from the IV characteristics, it is evident that switching is asymmetric. Generally, switching in forward direction is 14 to 18 volt. In reverse direction, it is slightly less, that is 7 to 9 volt. On-state voltage is also different in forward bias condition and in reverse bias condition. If it turns on in forward bias condition, that voltage is 7 to 10 volt, whereas in reverse bias condition it is only 1.6 volt. Switching current, one can see it is very low. It is 80 microamp and 160 microamp as shown in the figure. So therefore, for triggering also it does not require much current. ST4, since it is bidirectional device, one can use to produce pulses. One can see this circuit diagram where AC is given to the phase shifting network RC. R is variable and it is given to the ST4. As AC voltage changes, the phase changes, that's it will produce pulses as shown in the figure. When it triggers, that capacitor will discharge through ST4. It will produce pulses. ST4 can be used to produce pulses from the AC. The figure shows the circuit diagram in which there is AC source, there is DIAC, there is phase shifting network and output resistor. That AC is converted into the pulses which are bidirectional as shown in figure. If you see the timing waveforms of this is as shown in the figure. Depending upon the RC time constant, where R is a variable, the DIAC, depending upon RC time constant, the ST4 will trigger at different times. If you see the timing waveform, it is clearly seen that the phase shifting network produces delay to trigger ST4. If R value is higher, then there will be more delay, that is more phase angle to produce a triggering pulse. So this concept can be used for the triggering of the triac in light dimmer circuit as shown in figure. The working of this circuit is similar to DIAC as we have already seen. If we see the waveforms which are produced, these are the same as DIAC. We have seen two terminal devices, mainly DIAC, ST4 and Shockley diode. Now we will be studying the next device, that is a special types of transistors. There are two types of special type of transistors are used. First is UJT, that is unijunction transistor, and second is PUT, that is programmable unijunction transistor. These names are given because of their characteristics. Let us see the first device, that is unijunction transistor. Now we will be studying the unijunction transistor. These are the control devices. These are called as transistors, but unijunction. Why it is called unijunction? So one can be seen from the structure. UJT has three terminals. B2, B1, these are output terminals, and E is a control terminal, that is emitter. From the structure, one can see it is a rod type structure. It is a N-type substrate in which there is P-type of doping, but it is not diode because it has third terminal also. One can see this is a equivalent circuit. It is B2, B1 and E. E is connected in the structure, and RB2 is the generally resistance on the upper side of a UJT, that is BT to A to B1. So point A is not accessible to the user, emitter is accessible to the user. So one can see here this equivalent resistance RB2 is fixed, but RB1 is variable, so it varies. When diode turns on, its resistance goes down, otherwise RB1 is high. So from this one can see some mathematical equations which are useful for the designing of the circuits using UJT. So that is emitter voltage is equal to eta VBB plus VD, where VBB is the voltage applied between B2 and B1. VD is the diode voltage drop, generally it is 0.5 to 0.7. So what is eta? Eta is called as intrinsic standoff ratio. It is given by RB2 upon RB1 plus RB2. So this is fixed for UJT because this is because of the internal structure and internal resistance of the UJT. So that we cannot change this eta. This eta is a parameter for a given UJT. If you see the UJT characteristics, one can see there are three regions. First is the cutoff region, which is on the left hand side of the VEIE characteristics, and there is saturation region, which is at the extreme right position after valley point. So there are 2 points which are seen in this characteristics, peak point and valley point. If you see here, it is shown in red. It is called a negative resistance region because current decreases when voltage increases. So differential resistance is negative. So one can see this negative resistance region plays very important role for the triggering of the thyristor circuits. So there is peak voltage. So peak current is nothing but when voltage is at the peak, emitter voltage is at the peak, whatever current is there, it is called as peak current. Generally it is low. And valley current, one can see the valley structure in the IV characteristics. Therefore corresponding voltage and corresponding current is denoted by VV and IV, that is valley voltage and valley current. So emitter voltage, I is the emitter current, VP is the peak voltage, IP is the peak current, VV is the valley voltage and IV is the valley voltage. So UJT is widely used as a relaxation oscillator. Here component count is slightly higher than the two terminal devices. It has two external resistance and one RC circuit. Now if you see the working of this, when power supply is turned on, then capacitor will charge through the variable resistor. When emitter voltage reaches to eta VBB plus VD, so internal diode will turn on and current will flow from supply to ground through B2 and B1. So therefore, capacitor will discharge through B1. So therefore, voltage at B1 will be higher, but as capacitor discharges, the current will go on reducing. So therefore, you will get a pulse at the output as shown in the figure. Figure shows the capacitor voltage, that is emitter voltage, and base voltage. So these pulses are generally used to trigger thyristors. So there is another UJT which is called as PUT. It is a programmable unijunction transistor. You see the symbol, it is similar to SCR, but gate position is different. It has anode, it has cathode, it has gate which is connected to the upper terminal as shown in the figure. It has PNPN structure, 3 junctions J1, J2, J3. Its equivalent circuit is similar to SCR, but gate position is different as shown in the figure. It has IV characteristics completely similar as UJT. So therefore, it is called as unijunction transistor. In fact, it has 3 junctions, but its characteristics is similar to UJT. Therefore, it is called as programmable unijunction transistor. So why it is called as a programmable? So that we will see afterward. So V is the anode voltage, I is the anode current, Vp is the peak voltage, Ip is the peak current, V is the valley voltage, and IV is the valley current. It is similar to UJT. Now we will see the application of PUT as a relaxation oscillator. When power turns on, capacitor will get charged. When voltage at anode becomes greater than gate voltage by 0.5 volt, that is one junction drop, then PUT will turn on and capacitor will discharge, producing pulse at the output. Now here the triggering voltage will be decided by the gate voltage, and gate voltage is decided by the potential arrangement of R1 and R2. The timing waveforms are as shown in the figure. It is similar to UJT, so therefore you will get the pulses at the output. This can be used for thyristor triggering. Now these are the formulas. One can see Vp peak voltage is R2 upon R1 plus R2 into Vs. This is approximate voltages. Now one can see the eta, that is intrinsic standoff ratio. Intrinsic standoff ratio is given by peak voltage divided by the supply voltage. Now from this equation one can see that it is R2 upon R1 plus R2, and R1, R2 are external resistors. It means one can program the value of eta. So that's why it is called as programmable unijunction transistor. The designing formulas are shown. Now next control device is silicon unilateral switch. It is also called as SUS. It has 3 terminals: anode, cathode and gate. The symbol is as shown in the figure. Its equivalent circuit is combination of transistors PNP, NPN, but it has additional, that is Zener across a NPN transistor as shown in the figure. Now we will see the SUS characteristics. One can see it is similar to Shockley diode. The difference is one can change the forward breaker voltage, that is Vs. that you can change by gate triggering. But in general, practically people don't prefer the triggering in this case. So, VR is the reverse breakdown voltage, Vs is the forward switching voltage, If is the rated maximum forward current, If is the holding current. One can see these values are low. So, generally forward breaker voltage is 8 volt, reverse voltage is typically 30 volt. Now, the main application of SUS is a relaxation oscillator, which is shown in the figure. One can see the component count is less. So, here in this case, gate terminal is not used practically. Now, the working of this is similar to the previous devices. Capacitor charges when power turns on. When it reaches to the forward breaker voltage, capacitor will discharge, producing a pulse at the output. Slide 52. Next device is silicon control switch, SCS. It has 4 terminals, anode and cathode, but it has 2 gate terminals. First is anode gate and second is cathode gate. Cathode gate is near to cathode, anode gate is near to the anode. The structure is PNPN with 2 gates as shown in the figure. Its equivalent circuit is similar to SCR with additional gate. Now, if you see the forward characteristics, which is more important, it is similar to SUS. Its main application is relaxation oscillator. One can see this circuit. So, it is similar to PUT. So, here when capacitor reaches to some particular value which is greater than the anode gate voltage, it will turn on. Till that time it will be turned off. Therefore, it will produce a pulse. When gate voltage is greater than anode voltage, then it is off, and if cathode gate voltage is greater than cathode, then it will turn on. There are various ways to turn on and turn off the SCS. In this application, only one gate is used for the control. The next terminal, that is cathode gate, which is kept open. Silicon bilateral switch, it is also called as SBS. It has 3 terminals, anode 1, anode 2, these are main terminal, gate is a control terminal. The equivalent circuit which is shown in the figure, one can see it is similar to SUS. It is a combination of 2 SUS. Now, SDS characteristics. Now, one can see this characteristics is generally symmetric. The switching voltages are same in forward direction and reverse direction also. In the diagram, IF is the rated maximum forward current, IS is the holding current, ES is the forward switching current. So, one can see this, the triggering current is very less. So, therefore, it is widely used. The values of IF, IH and VH are virtually identical in the first quadrant except for the polarity. So, this is a circuit which will produce the pulses at the output. So, input is AC and SBS is connected as shown in the figure. Control terminal is not used for this circuit. So, it is used as a 2 terminal device. So, it will produce pulses at the output. These pulses can be used for further switching of SCRs or triacs. So, working is similar because this circuit is similar to the previous ones. Let us summarize this session. In this session, we have studied special triggering devices. These devices are used for thyristor triggering. These devices are classified as diodes, multilayer control devices, and unijunction transistors. We have seen the IV characteristics of these devices as well as the working of these devices. We also studied some circuits which are used in practical applications. In general, we have mainly studied the relaxation oscillator as an application circuit. All these applications are easily possible because of negative resistance region of these devices.